Today, something is being picked up by a spacecraft over 13 billion miles from Earth, and almost nobody outside of the scientific community is talking about it properly. Voyager 2, a probe that was built using technology from the early 1970s and launched in 1977, is currently sailing through interstellar space, the region beyond the edge of our solar system, and its instruments are detecting a persistent frequency, not a random burst of noise, not a one-time glitch, a continuous measurable signal humming through the plasma of interstellar space that has been present every single time scientists have looked for it since the instruments first picked it up. And what that frequency is telling scientists about the space between the stars is reshaping the models that physicists have built over decades to describe what interstellar space actually is. To understand why this matters as much as it does, you need to understand what Voyager 2 actually is, where it actually is right now, and what it has been doing in the space between the stars since it crossed the heliopause on November 5th, 2018. Voyager 2 was launched on August 20th, 1977. 17 days before its twin, Voyager 1, even though it carries the number 2. The reason for that is trajectory. Voyager 2 was sent on a longer, slower path specifically designed to take advantage of a rare alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that happens once every 176 years. NASA called it the Grand Tour. One spacecraft, 4 planets, a single mission that exploited a once in almost 2 centuries cosmic coincidence to give humanity its first, and to this day, only close-up view of all 4 giant worlds. Voyager 1 took a faster route, skipping Uranus and Neptune but reaching interstellar space sooner. Voyager 2 reached its final planetary destination, Neptune, in 1989 and then kept going. It has been going ever since. The mission was supposed to last 5 years. Voyager 2 is now nearly 49 years into it. As of mid-2025, Voyager 2 is approximately 143 astronomical units from the Sun. That is, more than 13 billion miles. At the speed of light, a radio signal from Earth takes about 19 hours just to reach it, another 19 hours for any response to get back. So when scientists send a command, they wait nearly 40 hours round trip to find out what happened. Every instruction, every data request, every power management decision operates on that delay. The power situation is the thing that defines everything about the Voyager mission in 2026. Both probes run on radioisotope thermoelectric generators, nuclear batteries that convert the heat from decaying plutonium-238 into electricity. When Voyager 2 launched in 1977, those generators were producing around 470 watts. Every year, since as the plutonium continues to decay, that output has dropped by about 4 watts per year. After nearly half a century, the margin is razor thin. Every watt has to be accounted for. Heaters have been shut off. Backup systems have been cut. Science instruments have been deactivated one at a time in a carefully planned sequence that the engineering team at JPL has been managing for years. As of 2026, Voyager 2 is running 3 science instruments: the magnetometer, the Plasma Wave Subsystem, and the Cosmic Ray Subsystem. Just 3 instruments remaining on a spacecraft that launched with 10. And it is the Plasma Wave Subsystem, the instrument that detects oscillations in the charged gas surrounding the spacecraft. That is at the center of what makes this frequency detection so significant. Here is what is actually happening out there. And this is where the story gets genuinely extraordinary. Interstellar space is not empty. That is one of the things the Voyager probes have made completely clear. Beyond the heliopause, beyond the protective bubble that the sun's solar wind inflates around our entire solar system, there is a medium, a very local interstellar medium, scientists call it. A thin, cold, diffuse gas of charged particles threaded through with magnetic fields that have been carried there by plasma ejected from dying stars across billions of years of galactic history. And that medium has a frequency, a persistent narrowband signal that the plasma wave instruments aboard the Voyager probes have been detecting as the spacecraft drift through it. It works like this. Plasma, the fourth state of matter, a gas where electrons have been stripped from atoms, oscillates at a characteristic frequency determined by how densely packed the electrons are. It is called the plasma frequency. And when Voyager's Plasma Wave Subsystem detects that frequency, it is essentially taking the pulse of the interstellar medium, measuring how many electrons per cubic centimeter surround the spacecraft at that moment. Voyager 1 first detected the signal reliably beginning in 2017, 5 years after it crossed the heliopause. The Cornell University research team that identified it, led by doctoral researcher Stella Koch-Ocker, published the results in Nature Astronomy in 2021. What they found was a persistent, very weak, narrowband plasma wave emission, a steady hum, at a frequency of around 3 kilohertz, detectable continuously between observations made during solar storm events that had previously been the only way scientists could measure the interstellar plasma density. The signal was always there. It just required careful analysis to hear it under the noise. That 3 kilohertz tone corresponds to an electron density of approximately 0.111 electrons per cubic centimeter, a figure that matches closely with independent estimates of the density of the local interstellar cloud, the particular region of interstellar space our solar system is currently moving through, derived from measurements of carbon absorption lines in the light from nearby stars. In other words, Voyager was measuring the local interstellar medium from the inside, and the number it was getting matched the number astronomers had estimated from billions of miles away by looking at the shadows of distant stars. Both measurements agree. The frequency is real, and it is consistent. What Voyager 2 adds to this picture is the second data point in a second direction. Voyager 1 crossed the heliopause heading roughly northward out of the plane of the solar system. Voyager 2 crossed heading roughly southward, on a completely different trajectory through a completely different region of the heliosphere boundary. The fact that the same persistent plasma frequency is detectable by both spacecraft in 2 different directions tells scientists that this signal is not a local quirk of one particular exit route out of the solar system. It is a property of the interstellar medium itself, surrounding our solar system on multiple sides. That matters for a specific and important reason. The heliosphere, the protective bubble the sun creates around our solar system, is not uniform. The 2 Voyager spacecraft saw structurally different behavior at the heliopause when they each crossed it. Voyager 1 detected dramatic magnetic field fluctuations right at the boundary. Voyager 2 did not. The plasma conditions on the 2 sides of the solar system are measurably different. But the persistent plasma frequency, the interstellar hum, shows up in both directions at roughly comparable electron densities. That tells scientists that whatever local differences exist at the boundary, the deeper interstellar medium surrounding us has a consistent underlying structure. And measuring how that frequency changes over time and distance as the Voyager probes continue moving outward is allowing scientists to build the first direct in situ map of density fluctuations in the very local interstellar medium. Not an estimate, not a model extrapolated from telescope observations, a direct measurement from instruments physically embedded in the medium being measured, moving through it at roughly 34,000 miles per hour, sampling it continuously. The density fluctuations that show up in that data reveal something else entirely. Turbulence. The interstellar medium is not a smooth, uniform gas. It is turbulent at scales of astronomical units, meaning that over distances comparable to the span of our entire solar system, the density of interstellar plasma fluctuates measurably. That turbulence affects how cosmic rays propagate through interstellar space. It affects how signals from distant astronomical objects are scattered and dispersed before reaching Earth. Understanding the structure of that turbulence at the scale Voyager can sample it directly is something no other instrument in existence can provide. There is no substitute for what these probes are doing. Every other measurement of the interstellar medium is indirect. Telescopes can study absorption patterns in starlight and infer what the gas between the stars must be doing. Instruments like NASA's Interstellar Boundary Explorer can detect energetic neutral atoms streaming back inward from the heliopause and reconstruct what the boundary looks like from the inside. But Voyager 2 is physically sitting in the interstellar medium, physically surrounded by it, physically measuring it from the inside with an instrument that is still working after 49 years. There's nothing else like it, and there will not be for a very long time. The next mission, capable of making direct in-situ measurements of interstellar space, would need to be launched now and travel for decades before reaching the distances Voyager 2 is at today, and no such mission is currently funded or in development. So, every day that Voyager 2's Plasma Wave Subsystem continues to function is another day of data that could not be obtained any other way. Every frequency measurement is a data point in a record that is, right now, completely unique in human history. The signals arriving at the Deep Space Network antennas in California, Spain, and Australia carry that data at a rate of 160 bits per second, a data rate comparable to a 1990s dial-up internet connection. Transmitted by a radio with 23 watts of power, roughly the same as a refrigerator light bulb, spread across 13 billion miles of space by the time it reaches Earth. Engineers at JPL manage that trickle with the kind of precision that is extremely difficult to appreciate unless you sit with the numbers for a moment. They have been doing it for nearly half a century. Some of them have spent their entire careers on this mission. Some of them were not born when it launched. And what those engineers have kept alive out there in the dark between the stars is something that changes what we know every single time it sends back another measurement. A frequency from outside our solar system, a steady hum in the interstellar plasma, a signal that confirms the medium surrounding our sun is real, structured, turbulent, and measurable, and a 49-year-old spacecraft, built with 1970s technology, running on the power of a light bulb. That is the only instrument in existence capable of measuring it from the inside. That is what Voyager 2 is detecting right now, and it is going to keep detecting it for as long as the hardware holds together And the engineering team at JPL keeps finding ways to keep one more instrument running for one more year. What makes the frequency finding land differently than most space discoveries is the scale of what it implies. The hum of interstellar plasma that Voyager 2 is measuring is not a local sound. It is the sound of the galaxy itself. The electrons oscillating at 3 kilohertz around that spacecraft were not put there by anything our sun did. They were seeded there across billions of years by the death of other stars, by supernovae that exploded before our solar system existed, by processes operating on timescales that make the entire history of life on Earth look like a brief flash. Voyager 2 is drifting through that, taking its temperature, sampling its density, and sending the numbers home at 160 bits per second through a 19-hour signal path to a team of engineers who wake up every day and figure out how to keep the instrument alive for one more year. The engineering team has stated that if both Voyagers remain healthy, the mission could continue with at least one science instrument running into the early 2030s. Voyager 2 will not reach 1 light day distance from Earth until November 2035. Whether it is still operating by then is uncertain. But based on everything the team has managed to do so far, including the Big Bang power overhaul confirmed successful in August 2026 that bought the 3 remaining instruments at least another year of life, the safest bet is to stop underestimating this spacecraft. It has been defying expectations for 49 years. It crossed a boundary no probe had crossed before. It measured temperatures at the heliopause that the models had not predicted. It confirmed a persistent plasma frequency in the interstellar medium that now allows scientists to map the density of the space between the stars in real time. And it is still going. The universe beyond the heliopause keeps turning out to be stranger and more structured than the models predicted. And Voyager 2 is still the only thing we have out there listening.